thanks for watching, and today I will show you why people really care about partial derivatives and tangent planes. Because it helps us to approximate very complicated functions. And in fact, this leads me to today's topic, which is linear approximations and differentials in the multivariable sense. But you'll see it's almost identical to the single variable case. So for instance, let's do the following example. Take the function f of xy, which is square root of xy. And the first question is, let's find the linear approximation called L of xy of f at the point 1, 4. Now, strictly speaking, I'm supposed to draw a three-dimensional figure, but just to make things a little bit clearer, let's have a profile view of the function. Kind of like a Facebook profile picture of what's happening. So suppose this axis represents all the points xy. So it's supposed to be a plane at the bottom, and z is the third axis. Then what do we have? On the one hand, we have our function. Kind of looks like that. So f of xy, it's square root of xy. Again, think a three-dimensional version of this. On the other hand, at the point 1, 4, we have the tangent plane. And the idea is, well, I'll tell you in a second. So this is the tangent plane. Let me make it clear, it goes to the point. So pretty close. And again, I want to emphasize this is supposed to be a three-dimensional thing. So in general, f might look something like that. And you have the tangent plane, which is a plane kissing the function at the point 1, 4 or something. This is like the three-dimensional version of what is happening here. And what's the idea? The idea is, near the point 1, 4, the tangent plane is pretty close to your function. In fact, if you look at it here, it's almost indistinguishable. Modulo my bad drawings. But the point is, they're supposed to be very close, and that's why we give a very specific equation to this tangent plane. It's what's called the linear approximation. So given a point xy, the height here, it's called L of xy, as opposed to the height of f, which is f of xy. So in other words, L is nothing else than the equation of the tangent plane. So definition, L of xy, again, it's just the equation of the tangent plane at 1, 4, which is nothing other than f of 1, 4 plus fx of 1, 4 times x minus 1 plus fy of 1, 4 times y minus 4. Again, think like a point plus the slope times x minus a plus another slope times y minus b. So very similar to the single variable calculus definition, which simply is f of a plus f prime of a times x minus a. So you see, just a developed version of this. And well, let's calculate it in this case. So again, right now, I will draw this picture again, so don't worry. Okay, so f of 1, 4, that's square root of 1 times 4, and that's square root of 4, which is 2. Now, let's calculate fx. That is square root, again, of, you have to be a bit careful, xy with respect to x. And that becomes 1 over 2 square root of xy. And you differentiate that with respect to x, which becomes y. And in particular, I know you can simplify this, but since we just want it at a point fx of 1, 4, that becomes 4 over 2 times square root of 4. And I believe this becomes 1. Yes? And let's do the same thing for fy. That becomes square root of xy with respect to y. And that's 1 over 2 square root of xy times the derivative of this with respect to y, which is x. And therefore, fy at the point 1, 4, that becomes 1 over 2 square root of 4, which just becomes 1/4 in this case. So plugging this back in, we get L of xy equals 2 plus 1 times x minus 1, so 2 plus x minus 1 plus 1/4 times y minus 4. So again, that's the equation of the linear approximation, or just the tangent plane of the function f at 1, 4. Now, so far we've done nothing new. We just found the equation of the tangent plane, but now let me tell you why it's so useful. Because suppose you're stranded on an island and you don't have calculators. No problem. Using this, we can actually approximate very complicated values. So use L of xy to approximate square root of this really complicated number, 1.01, and then 4.02. And again, I don't know much history, but I'm guessing that's also how people did it back then. So before they had calculators. And you'll see it's not too bad. So, notice first of all, what is this in terms of f? This is f of 1.01 and 4.02. Now, in other words, what does L have to do at all with f? Well, here's a very nice fact. In other words, for xy near your point 1, 4, L of xy is actually roughly equal to f of xy. In other words, L is a pretty good approximation for f, at least for points that are close enough to 1, 4. So let me illustrate this again with this picture I drew. So again, here we have xy. And we had our starting point 1, 4. We have our function. So that is f. And we have our linear approximation, L. L. And again, the whole point is, well, okay, L and f are equal at 1, 4. But if you take a point nearby, say 1.01 and 4.02, then those two values are almost the same. 1.01 and 4.02, and this is L of 1.01, 4.02. Well, those two, as I said, they're very close to each other. In other words, this thing here, it's pretty small. So this error here, it's a small error. And using this, we can actually approximate this complicated value. Because you have to understand, f is very complicated. It has a bunch of square roots in them, but L is not complicated at all. It's just a linear function. So in particular, this value will be very easy to calculate, and therefore this value is very easy to be approximated. That's the main gist of it. And I do want to say something kind of interesting about that. So in this case, L is pretty close to f. That is not always true. So there are some weird functions for which this is not true. But surprisingly, and that's kind of the coolest thing about this is actually the definition of f being differentiable. Forget about partial derivatives for a second. Even without partial derivatives, you always have this tangent plane. But the definition of being differentiable is precisely that f is close enough to your tangent plane. So something purely geometric, and the nice thing is you can show, I believe, it's equivalent to having continuous partial derivatives, so that they exist at the point, and I believe they're continuous near the point. This is cool mathematically, but let me go back to our problem. So how can we now solve our thing? Well, not too bad actually, because look, our square root business, square root of 1.01, 4.02, that is f of 1.01, 4.02. But as I said, that's approximately equal to L of 1.01, 4.02. But L, remember, has this very easy definition. That is 2 plus 1.01 minus 1 plus 1/4 4.02 minus 4. Okay, that's by A. And then what this becomes, it's 0.01 plus 0.02 over 4, and that's 2 plus 0.01 plus 0.005, and I believe you get 2.015. Which, by the way, is very close to the actual answer, which is, at least on the calculator, you get 2.014994, blah, blah, blah. So not even pennies away from the actual answer. So that's pretty good. I love when math works out like that. All right. And in fact, you might get even better answers once you get even closer to the point 1.04. All right, so that is one way of looking at, approximate values and linear approximations. The other side of the coin, and I want to emphasize it's precisely the same thing, is by using what's called errors or differentials. Even though differentials is a bad term, it's also used for something else in math with vector fields. But let's do the same problem, but using differentials. To approximate against square root of 1.01 and 4.02. So again, as before, your function is just square root of xy, and your point, it's simply 1, 4. Something close to 1, 4 here. And as I said, another way of looking at this process is by using errors. So instead of saying L is close to F, we just say the error by using L is small. And for this, unfortunately, we need a little bit of notation. So let me draw a nice big picture here. So we first have 1, 4. and the point 1.01 and 4.02. Now, already in x and y, we have a certain error. Because 1.01, that's not 1, but kind of close to 1. And this error here, we call this dx and dy. So, notation. So dx, also called delta x in this case, it's 1.01 minus 1, which is 0.01. Again, that's the error in x. On the other hand, we have the error in y, which is 4.02 minus 4, which is 0.02. Okay, that's one thing. And then now let's look at f. So we have our function f here, f of xy. Now, on the one hand, we have f of xy. So I'm sorry, f of, let's say, 1, 4. So f at your starting point, and then we have f at the ending point, which is here. F of 1.01, 4.02. And forget about linear approximations for a second. So even without doing this, well, one way we can approximate this is just doing f of 1.01, this value minus this value. And that is, if you want the actual error by using this close point. And we call that delta z. And that's literally f of the end minus f of the beginning. That's f of 1.01, 4.02, minus f of 1.4. And what this becomes, it's square root of 1.01, 4.02, minus square root of 1 times 4, which is just square root of 1.01, 4.02, minus 2. And again, that is the actual error in our measurement. So really, the f of end minus f of the beginning. And notice, so far we did not use any linear approximation whatsoever. We just use f itself. Now is where L comes in. So suppose again we have at the point, and we have this nice tangent line, right? L of xy. Well, as I said, you could also approximate f by using L of 1.01, 4.02, which is here somewhere. Notice, if you're using L, then you also have a certain error. You know, L is not the same as f as your starting point. So in fact, here, you have a bigger error, and you call this dz. I know, because all this notation is really making me dizzy, okay? And so definition, dz, which I like to call a calculus error, is just, by definition, just fx 1,4 dx plus fy 1,4 dy. So if one, that's a calculus error. So in other words, it's just the error by using L instead of f. So in other words, all that this is, it's the same thing as using L of 1.01, 4.02 minus f of 1, 4. So again, delta z is the actual error in your measurement. dz, it's a calculus error. It's the one by using L. And in this case, concretely, what this becomes, dz that is, in this case, 1 times, we found dx to be 0.01 plus 1/4 times 0.02, and this becomes 0.050. Now, I know this notation, it's driving me crazy as well, but what's the point? The point is, we have this actual error that's very difficult to calculate because we need to know that, but we have the calculus error that we calculated in almost 2 seconds or something. And the point is, of course here we have an exaggeration, but in theory, those two things, they're very close to each other. And even better, provided your point is closer. So here's the fact, which again is equivalent to saying L is close to F. It's simply that dz, it's approximately equal to delta z. Or in other words, delta z is approximately equal to dz. At least if dx and dy are small enough. And that helps us calculate this, because what it is saying is 1.01 times 4.02 minus 2 is roughly equal to 0.015. And so square root of 1.01, 4.02, it's roughly equal to 2.015. So you see, kind of the same answer that we got before, but this time using those differentials. So to do the problem, it's always the same thing. You calculate delta z, which is f of end minus f of start. You calculate dz using this formula, and then you just do a little bit of algebra. Alright, I hope you liked this little linear approximation / differentials extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.